nanohub.org.
So I'm John Melcher, and I'm going to talk today about, give you guys an introduction to VEDA, which is a virtual environment for dynamic atomic force microscopy. And I'm one of several people in Professor Raman's group, which has been developing these simulation tools. So an overview, what is VEDA? It's an open source simulator for dynamic AFM, which simulates most of the important experiments that we would do in AFM. It's open source, so you can download the source code if you want to and modify it. But also it's accessible freely from NanoHub, which means you can just simply log on to NanoHub's website and run it on their machines from your computer. So you can actually just run it through a web browser. The second thing I'd like to discuss briefly before we get started is why do we want to do simulations in AFM? And I thought of a few reasons I wrote down. We can always do the experiment, but some of the issues with the experiment are that it may involve unanticipated elements. So for instance, we think our sample is a hard substrate, like mica or graphite, but actually there's some condensate that forms, there's a liquid layer that forms on the substrate which affects our results that we don't know about. Or for instance, we attempt to do a force distance curve, but when we apply the voltage to the piezo, there's some creep in the piezo. So there's always these unanticipated elements in the experiment which can give us headaches, and it's nice to do simulations for that reason. Also, the experiments have limited observables. The idea is, what are the measurements that we make in the experiment, and what physically is happening to the AFM during the experiment. This will become much more evident when when you guys get to dynamic AFM, where the cantilever is vibrating and intermittently contacting the sample. But it's just something to keep in mind. So the simulations are useful because, one, we have a controlled environment. We know exactly what's going to happen, and it's up to us to interpret the results of the simulation, but we know that the sample is what we specified in the inputs to the simulation. We have a very controlled environment. And secondly, we have information beyond what the observables in AFM record. So things like indentation and contact times, specifically, several of these will be more relevant to dynamic AFM, but just something to keep in mind. Okay, and before getting started, I'd just like to go over some preliminaries so that we're on the same page. So the AFM involves a cantilever on a chip, and we make the measurement of deflection by reflecting a laser off of the tip of the cantilever, and it's captured by a quadrature photodiode. And in terms of the experiment, what we know is the elongation of what we call the Z piezo, which is basically displacement of the base of the cantilever, and we know the deflection. We measure the bending angle of the cantilever, which we equate to deflection. But in terms of the simulation, the nice things so we're going to talk about Z, which is the position of the base, but also the instantaneous tip sample gap between the tip and the sample. And the deflection will be, or observed deflection will be, what the photodiode measures from inferring deflection from the rotation angle. Okay, so with that, if you guys are on nanohub.org, the first step is to locate VEDA's website, or the page for VEDA. And to do that, if we go to resources, you'll see there's a drop-down menu which lists several resources on VEDA, such as lectures and notes and presentations and so forth. And among those is tools, which is where all the simulation tools are located. So we'll select that. And here there's a menu item. If you browse down on the list of if you find atomic force microscopy, you should be able to find VEDA from there. And we can go to the website. I think actually there's one of the tags was damaged, so maybe you select all and you'll have to scroll down through everything to find VEDA. But so some indication you guys are on the right track.
Is everybody on, anybody not on VEDA website?
Okay, great. Okay, and let's first select, so don't launch the tool yet, but let's select the link at the top. And that will take us to a web page for VEDA. And so on the website,
John, can you hold on a second?
Yeah.
Some of them clicked launch.
Okay.
So please go back.
You jumped the gun.
What do you want them to, can you repeat again?
Okay, if you
Where
would
do you want them to click?
select the link at the top.
Which link? Can you please highlight it?
So the link at the top will take you to VEDA's web page first.
Can you move the cursor to what do you mean link? Which link are you talking about?
This link over on the left.
What does it lead them to?
It leads them to the web page for VEDA.
No, that's not what.
This is what John's talking about.
Yeah. Okay. Yeah. Okay.
Okay. So on VEDA's website, you'll find some useful information. Specifically, there's supporting documents, which is a very detailed manual, which includes all the models that are used in VEDA and several examples.
All of you have a copy of the manual. It was given to you in the first week.
Okay, okay, and so from there, from the website, we can actually select to launch the tool. Okay.
Good. Yeah.
And sometimes there are issues with Java if you don't have the latest version installed. So if anybody's having trouble loading the tool, let me know.
Everybody get this symbol turn up? Okay.
Okay, great. So what can VEDA do? If you'll note, there's a drop-down menu up at the top of the simulator after the introduction page, and from the drop-down menu there are several tools listed. And for instance, the first tool is the Force Viewer tool, which allows us simply to plot a tip-sample interaction model for some given properties that we'll enter. There's a Force Distance Curve tool, which is what we're going to be covering today, which allows us to do a quasi-static approach curve and touch the sample and retract. And then the remaining ones are dynamic AFM, such as amplitude modulation approach curves and frequency modulation approach curves. We can even do scanning in quasi-static or in dynamic AFM. And finally, a frequency sweep tool. But since we haven't covered dynamic AFM yet in the course, we won't worry too much about that. We're going to focus on the tip sample force viewer and the force distance curve tool. Oops. Okay, so let's select the tip sample force viewer tool. From that drop-down menu on the previous page. Okay.
Hold on. Let's check to see if everybody got there.
All right.
Everybody got there? Anybody not got there? Do we need to get up and look at everybody's screens, or can you raise your hands if you don't get there? Please?
So at any point in time, if you guys are behind one, just
please raise your hand. Otherwise,
just raise your hand and I'll pause. Okay.
Because if you get left behind, you won't, for some reason, you won't catch up. So.
Right. Okay, so when we select this, you'll notice that there are tabs at the top of the page, and these have different input parameters on them. The first one that comes up is the what we call operating conditions, and for this, I just want to change the input for the initial gap to 5 nanometers and the final gap to -1 nanometers from the default inputs. Okay. And second, if we select the tip sample interaction properties tab, you'll find...
John, they did not enter those numbers. Can you please go back? Right, make sure you're asking them to enter 5 minus 1 in there. Do you want them to do that?
Yes.
Okay, so please give that instruction.
Yeah, so if you can change the defaults from, I think it's 10 and 0 to 5 and minus 1 for the initial gap and the final gap in the first two. So does everybody have that?
So the initial gap means how far the tip is above the sub?
Yeah, and this is the tip sample gap. Since we're just plotting a force viewer, we're not doing a simulation yet. This is just to demonstrate the what the interaction model we're going to use that covers forces between the tip and the sample. Okay?
So if the final gap is minus 1, you're going to penetrate the sample?
Yes, correct. So initially we'll be above the sample surface, and then minus 1 will be indented.
So these are basically the FD curves, okay? Not FC,
Right.
just FD so far.
And we're simply plotting a model here. We're not doing a simulation yet. Okay, so let's select the tip sample interaction properties tab. Okay. And from here, a page comes up and there's a drop-down menu for tip sample interaction model. So if you click the drop-down menu, you'll find that there are several interaction models are listed here. So this is how we're going to model the relationship between the position, the gap D, and the force exerted between the tip and the sample. So there's several options here for, depending on what the composition of the sample is, that we can choose that help to model our experiment. Let's select the DMT contact model. Okay. And doing that, the first thing that comes up is this picture. So for each interaction model, there's a simple schematic which shows qualitatively what the interaction model looks like. The DMT contact model involves an attractive regime, which is given by a negative interaction force, and modeled by van der Waals attractive forces between the tip and the sample. And then at some separation, A0, which we call the intermolecular gap, is the onset of repulsive forces. And we assume this is continuous, but it works out to be non-smooth. And then after we start indenting the sample, the repulsive forces are modeled by a Hertz contact mechanics. So for any gap less than A0, we're said to be in contact with the sample. Okay, and second, note this scroll bar on the side. There's actually input parameters hiding at the bottom of the, if you will scroll down, you'll find the input parameters which are relevant for the DMT model. And you'll notice that there are several other inputs which are grayed out, and those are basically input parameters for other models which are disabled when we select the DMT model. So the inputs for the DMT model are, for instance, the tip radius, the radius of the tip, the Young's modulus of the, and Poisson's ratios of the, both the tip and the sample, and Hamaker constants. Okay, and the elastic moduli and Poisson's ratios have to do with the Hertz contact forces, and the van der Waals, or the Hamaker constant and tip radius, and has to do with the van der Waals forces. Okay, but we're going to keep all the defaults here. So if you'll scroll, whoops. Okay, and so with that, we're going to select to simulate, which is the button at the bottom here. And the result that shows up is the tip sample force plotted versus tip sample gap. And this was for the DMT model, but it's for the specific
You're not getting it.
input parameters that you use. Okay.
Just go back. Can you guys go back to the input? Go down. Just press input on the bottom left if it doesn't come up. Yeah.
No.
Oh, it came up. Okay.
an influx of nano hub users.
The influx is going to be slower.
Okay.
So there's no little clock that tells.
For this one should be really fast because we're not actually crunching an ODE here.
So when I run this thing, I always get these blank screens. And it's like, I don't know whether it's computing.
Yeah.
There it is.
Okay.
There it is.
I think maybe it's either connection or the web browser.
There's no little clock that gives you feedback that it's actually doing it.
Yeah, the other, there should be a progress bar on the other tools, the ones that are doing more intensive calculations. The force distance curve really should take a second or two. Okay. Okay, so the first result that comes up, like I said, is the tip sample interaction force plotted versus tip sample gap separation. This is just the model that we chose for the specific input parameters that we chose. Okay. And if you take your mouse, you can actually mouse over the curve and it'll give you specific values for your interaction model. For instance, I'm going to the minimum interaction force, which we call the adhesion force, and it tells me that that's minus 1.4 nanonewtons, which is good because that was our input on the other page, so everything is okay. Also, this button up on the upper left corner, we can actually download this file. So if you want to download a PDF image file or a comma-separated text file, you have the option of downloading that, and maybe you want to plot it in your own software, use MATLAB or something. So you can make a professional-looking plot if you like. Okay. Okay, so with that, I'd like to move on to the force distance curves tool. So if we'll go back up to our drop-down menu for the application up at the top left, and select the force distance curves tool.
Go back to input.
So to the, back to, that's the input. Up at the top corner is the application drop-down menu. Okay. And from there, you'll notice that there is immediately below that is something called the example loader. Okay. And this allows us, so we've done some examples in the manual, and you can actually load all the inputs instantly if you select the example loader. So from there, let's pick, there's only one example for force distance curves, but let's pick example 1, approaching and retracting from the sample from the drop-down menu. Okay? And on the force distance curves tool, there's going to be more inputs now because we're actually going to be doing a simulation. So we have inputs regarding the operating conditions and the properties of the cantilever. For instance, the most relevant one here is going to be the stiffness of the cantilever, but there are several other operating conditions, for instance, the natural frequency and the quality factor of how damped the cantilever's motion is. Those become more important in the dynamic AFM, but we're actually simulating this full cantilever motion. So when we do the simulation, the cantilever is going to be able to vibrate depending on what inputs we give it and how harshly it hits the sample and so forth. So it's not just a spring at this point. So we're going to keep we loaded all these inputs, but they're on this page. Also, for instance, there's parameters like approaching the sample, what speed that we approach the sample with the base with, and what are the initial and final Z displacements. This is not the same thing as a tip sample gap. We're now specifying how the piezo actuates the cantilever in terms of the Z displacement. If you click on the the tip sample interaction properties tab, you'll find an input page that looks just like the Force Viewer tool. So, for instance, we still have our drop-down menu, and we can select the same tip sample interaction models. And here we're going to use the same DMT contact model from the Force Viewer example. Finally, there's a tab called Simulation Parameters, and here we have things like the number of points that we want to display from the simulation, and the number of points, for instance, that we're going to do in the simulation per oscillation cycle of the cantilever. That doesn't seem to apply here, but it's more for dynamic AFM. But how many points per period do we integrate for our differential equation? And one of the reasons, so the reason the points plotted is important is because the simulator is actually calculating hundreds of thousands of points. And if we display all those, it's really going to slow down the simulation, and it's going to make the file sizes huge and so forth. So that's limited here. So with that, if we'll select Simulate at the bottom right corner. And this simulation should run. And there's a progress bar. Okay, so are we all on the same page? Looks good. Okay. Okay, so
this is basically, now if you just look at the x-axis, it's z. So
yeah,
now,
so
it's FZ basically.
An important distinction. So from the drop-down menu of the results, if you'll select observed cantilever deflection versus z distance, I don't think it's the first one that comes up, but there's several plots generated in the simulation. If you'll select this one, and exactly now, the x-axis is the z displacement of the cantilever, and on the y-axis, this is what the measured deflection of the tip of the cantilever. And this is typically what you'll get in the force distance curves experiment, the first result that'll come up if you do this experimentally. And
So the model captures the channel.
yes, and that's my next point. So we are simulating a full differential equation. It's not just a spring, and so it's going to allow the cantilever to vibrate and snap into the sample. And that's what we see. We start approaching the sample from a far distance. There's basically no forces at first acting, or the forces are negligible at far away. And then as we get closer, you see the cantilever the tip starts to bend towards the sample under the influence of the attractive van der Waals forces. And at some point, the gradient of those forces exceeds the stiffness of the cantilever, and it snaps onto the sample. So it goes from being in a scenario which we would call non-contact to snapping into the surface of the sample and being in contact with the sample. And then from there, we approach further, and this almost looks like a 45-degree line when we're in contact with the sample, but there's some indentation on top of that line, causing a small deviation. Yes?
Which is the limitation, because if not, I don't have to do the test.
I'm sorry?
Why? Where are the limitations? What are the limitations of the model? Because if you solve all the differential equations,
we know the indentation, yeah. I
need to run a test, a real test.
Well, that's optimistic, I think. You probably do want to do the experiment to find ultimately to get the indentation in the experiment. Is that your question?
Well, I mean, the bottom line is this is based on a model where you know everything about the properties. If you know everything about the properties, why would you do this experiment?
Yeah, quite concisely.
Right, precisely. So this helps you sort of do some parameter studies where you can look to see, well, if For a soft surface, what's the best cantilever and so on. Yeah.
Mm-hmm. And it helps you develop an intuition. So one thing I should stress is that this is a nonlinear problem, so often that means non-intuitive. And it helps if we just do simulations to see what kind of things we expect, and then when we do the experiments, we don't think that the machine is malfunctioning. Okay. So as you probably, I believe you covered on Tuesday, the force displacement curve is not the same thing as the force distance curve. In force displacement, we mean force versus the displacement of the base of the cantilever. But a more fundamental property of the sample is the force versus gap curve. So what we want to do is basically subtract the deflection from the z distance, and we'll get something which represents the displacement of the tip. If we do that, if we select from the drop-down menu tip sample interaction force versus gap, we'll get this plot. Okay, and what you see is, you probably remember what the force versus gap curve looked when we used the force viewer tool to display it. You'll notice that there's a gap in our curve, right? So we come along, and all of a sudden there's missing information, right? Oh, and there's missing information. What's happened here is, as we were approaching, the tip snapped onto the sample. So there's that region where the tip went from in a non-contact state to contact state. We basically didn't get any information during that region. So,
did everybody get this versus gap? Yeah.
Okay. And that's just simply the reality of the force distance curve, the force distance experiment that we do, that if we have a snap-in, we're going to be missing some information from our force versus gap curve if we extract that. One thing you might try to do is use a stiffer cantilever, which avoids the snap-in, but the challenge with that is that it's less sensitive to forces if it's stiffer cantilever. So, and finally, if from the drop-down menu, if you'll select indentation, okay, and you'll notice that, so this plots how far the tip has penetrated the surface into the contact forces, and you'll notice that, so this is 0 when we're far away from the sample, but you'll notice that as we approach, it jumps up to a positive value. And that's what happens when the cantilever snaps into the sample. There's a discontinuous jump, or relatively speaking, in that indentation curve. So we don't start at indentation equal to 0. Because of the snap-in, we were already indenting the sample when the tip contacts it. And finally, we like to do, we can actually do the retraction curve. This got put out of order, I think. Yeah. Sorry. Okay, so if you go back to the previous page, I'm missing the input slide for this. But if you go back to the previous page, what you can do on the input for the operating conditions is we just want to invert the initial and the final z separation. Okay? Maybe I can do this on the web page. Oh, this doesn't look good. So if you go to the input panel, and you go to operating conditions, which is the first tab, and we want to change this initial separation to, I believe it was -1, and the final separation to, or So minus 10. Minus 5. Yeah. Okay. So this is going to do a retraction curve, right? So we're starting off at a smaller distance than we're stopping, and if we do this simulation, we're going to simulate the cantilever retracting from the sample. So is everybody on the same page? Okay, and if you go ahead and hit simulate after you do that, okay. Okay, and after you hit simulate, if you'll go down to the bottom corner and click all, it will display both of the curves from the two simulations that we've run on this page. And what happens if if you'll go down and select observed cantilever deflection versus z distance from the drop-down menu, what you'll see is there is a hysteresis in the cantilever deflection when we do the approach and retract. And this has to do with the fact that we start in contact, it takes a certain force for us to be able to remove the tip from the sample. And there's inevitably a region where the cantilever can be in either state depending on the initial conditions arises. So if we're at this range of tip sample gaps between about 0.5 nanometers and maybe 0.75 nanometers, then the cantilever can occupy one of two positions. Either it can be in the attractive van der Waals forces, or it can be snapped onto the sample, simply depending on the initial conditions. And again, if we are going to plot the force versus gap, still we have a separation where we don't have any information from. So there's still a region where the cantilever goes from contacting the sample as we're retracting, and then it pops off the sample. There's still a range of tip sample gaps where we don't measure any reliable information. Okay, so with that, I'd like to get into some problems, and the idea is we're going to give you a scenario that you're trying to prove, we're trying to understand using the simulation tool. Okay, and we'll give you a problem description. I'll let you guys have at doing a simulation to find the answer, and then I'll go over the solution that I came up with. Okay, so in this first problem, let's say you're trying to determine the elastic modulus of a soft sample. And the way we'll do this, I think probably you covered on Tuesday, was to try to fit the curve to a model, right? So you do some sort of nonlinear fit, and you'll get a parameter, assuming a model from a measured force distance curve. Okay? And when you do the model, we're going to have to assume, one, a model that we're going to use, but two, we need to know something about the geometry of the tip, and actually the properties of the tip. So we think that we have a tip radius of 10 nanometers, but unfortunately the tip has become degraded over use, and the tip radius is now more like 30 nanometers. So what will happen to our estimation of the elastic modulus if this is a scenario? So we're assuming 10 nanometers and the tip radius is actually 30. Okay? And use all the input parameters that we had from the previous example one, which are loaded. I want to make one exception though. If you'll go to the tip sample interaction properties tab, DMT is selected. Oh, I have two scroll bars. This is no good. If you'll deselect this parameter to auto-calculate the intermolecular distance, and we'll assume that it's just 0.2. It'll take the default value. So with that, other than that, we'll use the same inputs. Okay? All right. Okay, so I think everybody's good. So we'll go over the solution. So basically what we wanted to do was to do two force distance curves. In the first case, I think we already simulated was, we'll assume that the tip is 10 nanometers. And then in the second case, we'll do a simulation where the tip is what it actually is in the experiment, which is 30 nanometers. Okay? So the result is if you plot both of these curves, and on my computer, one of them is light and one of them is dark, but I guess it didn't come out well in the screen. But what happens is the shallow slope line is where the tip is 10 nanometers, and the steeper curve comes from the tip being 30 nanometers. There's two effects that happen here. One is that the adhesion force actually goes up for the tip being 30 nanometers because now the van der Waals forces are acting on a larger tip radius. And the other effect is that it stiffens the interaction, right? So now the tip is bigger and it's compressing more material when it interacts with the sample. So effectively it looks stiffer. So if we assume that the tip was 10 nanometers, and in actuality it's 30 nanometers, what we're going to do is we're going to overestimate the elastic modulus of the sample. And here it looks like it's about a factor of 2 that we're doing. It ends up being for the estimation of the elastic modulus. Okay? Any questions on problem 1? Are you looking at force versus gap or force versus deflection versus z distance?
Mine are offset. Okay.
Oh, yeah. Okay. So one thing I wanted to do was to change the input on to specify the intermolecular gap.
Did I miss that?
Yeah. So the default input was adhesion force. And specifying that is basically going to say when the tip gets bigger, the adhesion force goes up because the van der Waals are acting on more. So the intermolecular gap is almost more of a material property than the adhesion force. So.
Oh, so if you auto-calculate the
yeah,
difference, that lines them up somehow.
Yeah, so basically you've forced the adhesion force to be the same thing in both cases.
Then I have to run the simulation again.
Yeah. Okay, so with that, let's go on to problem number 2, which is cantilever selection. And in this problem, we're trying to determine the stiffness of a soft biological sample, such as a virus capsid. And we have some knowledge that if we apply more than 200 piconewtons, which is 0.2 nanonewtons, to the sample, that we're going to damage the fragile biological sample. So we don't want to do that. We have 3 choices of cantilevers. We're either going to use a 0.1 Newton per meter cantilever, a 1 Newton per meter cantilever, or a 10 Newton per meter cantilever. And the idea is, which cantilever should we choose to get the best measurement of the stiffness of the sample? Okay. And so for this example, we've been using the same tip sample interaction model, But if you go to the input parameters, let's use the interaction model, which says it's linear contact. So that means that there's just going to be a spring force, but it's going to start at some critical gap the spring sets in. And in the non-contact regime, the force is just zero. So we'll be approaching, and when we contact the sample, the forces will be modeled by a linear spring. Okay.
Is an option there, or is an option to do that, or is the model like that?
It's the model that we want to use. So if you go to tip sample interaction properties tab, DMT contact, and then select linear contact. I broke it. Okay, so select this model, linear contact, from the on the tip sample interaction properties tab.
So just to explain what linear contact means, just so, for some samples, and we haven't really talked about this when you do contact mechanics, but, our contact mechanics models have been Hertz contact, JKR, and, on Tuesday you heard Ryan talk about when you have, generalized Hertz contact for elliptical shapes contacting each other. But there are a lot of samples where your tip indents on something that is like a plate, a thin plate, or like a shell. So it's got a very thin sort of thickness. And so it's not like a solid bulk thing sitting on a sample. It's actually a suspended structure somehow. In those cases, the force distance curve is pretty much can be modeled as a spring, like a contact spring. You don't need to worry about this 3/2 power relationships. You don't have to worry about those things. And so a virus capsid is something like that. It's actually like a balloon, if you will. So it's actually the shape is very thin. The wall is very thin, and you're pressing down on a shell or a wall. And in these cases, the spring constant is a good representation of the force distance. So very simple. You just model what you're pressing as a spring. Okay?
Okay. Remember, you want to put in 0.5 Newton per meter for the stiffness of the sample. Okay, so Here's a solution for this problem. We did 3 different simulations for the 0.1 cantilever, and the result is that the softest cantilever is going to be the best cantilever. So that allows us to move more distance without exerting much force on the sample. So if we look at the curves, we imagine experimentally we're going to be acquiring data points at each z. We'd like to be able to move more z and without exerting so much force on the sample. If we use a very stiff cantilever, then we're basically just compressing the sample as we move z. And we have more data over more displacements, and it's more robust to experimental errors. Okay. And in this final example, we'll go back to, all these have to do with extracting material properties. We're trying to find the elastic modulus of a hard sample. In this case, this is something like mica with 60 gigapascals as the elastic modulus. And again, we have a choice of cantilevers of 0.1 Newton per meter, 1 Newton per meter, and 10 Newtons per meter. The sample is a solid, so we're going to model this with a Hertz contact model instead of the linear contact. And the restriction is that the actuation of our Z piezo is somewhat limited, right? And in the experiment, you can't specify any range of Z. You're going to have limits to the actuation of the Z piezo. So let's assume that we approach the sample, we locate the sample surface, and from here we can only transverse 10 nanometers from that point. So in your simulations, use Z final as minus 10 nanometers to represent the limitations of the Z piezo. And we'll do the 3 simulations for 0.1, 1 Newton per meter, and 10 Newton per meter cantilever. Okay? So use this model for your tip sample interaction.
Somehow we got to clear everything you already.
Oh, and I should mention that after you run a certain number of simulations, if you're transitioning to a new simulation or a new set of simulations, you want to clear out the old ones if you haven't saved them. Let's take a minute, but down at this bottom corner on the simulations tab, there's an option to clear the data. Okay? So on the results page, there's down at the bottom corner. And occasionally you want to do that. Just if you're changing too many parameters, it gets complicated in terms of the display. Okay.
The problem is we can't use the canned examples, right? We can't use the example loader.
Not for this. So these problems are not worked out.
Then you got to figure out what to type in.
Okay, yeah. So specifically,
That's the problem.
okay. Let's take the Hertz contact model. We'll use all the defaults except for the elastic modulus. In terms of the cantilever properties, we're just going to change K. We don't worry about the natural frequency or the quality factor or anything else. And for the Z displacement, just make sure that your final displacement is minus 10 nanometers and the initial one is something greater than 0, maybe 1 or 2. It's fine. Okay, So how are you guys coming? Good? That's good. Okay, so here's the solution. So if we use the soft cantilever, so the 0.1 Newton per meter cantilever, and from the drop-down menu, let's select, in terms of the results, let's select tip sample interaction force versus Z gap, okay? And this is the information depending on how you do the fit, but this is really the curve that we're trying to measure when we think about going from a measured force distance curve to a material property. The important curve here is that, how are the forces acting at different gaps? And what you see is if you use the soft cantilever here for the stiffness, given the fact that the Z actuation is limited, we're not going to be able to indent the sample very much, and we're not going to be able to extract a reliable material property. Basically, the sample looks like a rigid wall almost compared to the cantilever. So we come up, we press on it, and we're not able to indent the sample at all. We're not able to extract any meaningful data from this curve, right? And that comes from the fact that practically the Z actuation is limited. If we could just extend it forever, then eventually we would come up with a curve, but we can't do that. And so let's just look at the other extreme. If we use the 10 Newton per meter cantilever and we transverse the same base displacement, we'll be measuring a much more reliable data on this curve. So we're actually indenting the sample, and we're actually measuring data that has to do with force versus tip sample gap at this point. So these are two sort of extremes. You think maybe to do the force distance curve, we want the softest cantilever, so the most sensitive cantilever, but because of these practical limitations, like the Z actuation, we want a cantilever which has sort of a similar stiffness to the sample that we're measuring, actually. So that's how it sort of works out. In the end of the day, is you want your cantilever to have a somewhat similar stiffness to the sample, and that's because of the combination of the measurement errors and the limitations on the Z actuation of the piezo. Okay? Does that make sense to everybody? All right, good. Okay, so that's the last example we want to do today. And yes, so the 10 Newton per meter cantilever is the best. Once again, my name is John Melcher, and I'm one of the developers for VEDA. So I've written a good amount of the simulation codes and the models that are in VEDA. So if you're having some trouble with an input or modeling something, you can reach me at my email, which is jmelcher@purdue.edu. Okay? Thank you.